Hey guys, not sure if you ever heard that, but there's this one thing that's like this mythical creature in computer graphics, and it's called the Mandelbrot set. And the Mandelbrot set is one of the prime examples of fractals, and it's what started all the fractal craze back in the 80s and 90s. And what we're going to do today is not only implement a Mandelbrot set, but also implement its more modern, more three-dimensional cousin, the Mandelbulb. I will not go into the math of things. If you're interested in it, and it's a weird math, and quite an interesting one, I can wholeheartedly recommend this YouTube channel by Daniel Schiffman. He's got 2 videos on implementing the Mandelbrot set and the underlying math behind it. And he's really a quirky guy. It's really fun watching his videos, and those are quite good programming tutorials. So even if you're not interested into fractals or Mandelbrot, you should definitely watch Daniel Schiffman's YouTube channel. So the general algorithm for Mandelbrot figures or Mandelbrot sets that we're going to implement goes like this. On a set of points in a plane on a regular grid, for each point's position x and y, we execute these 2 formulas. And again, I'm not going to go into detail about how to come up with those formulas and what they actually represent. I highly recommend watching Daniel Schiffman's video on the Mandelbrot set if you want to get deeper insight in what they actually mean. He does a really good job at explaining the math behind it. But what we're going to do for each point is we just going to feed the points x and y into these formulas, and for each point we're going to run over these formulas for a given number of loops. So we're going to loop those formulas, and we will have a look at the resulting value coming out here of those 2 formulas. We'll check if these values are going to infinity or not, so if they become really big or not. And we will just color these points differently depending on if those results of the formulas will tend to go to infinity or if they don't go to infinity. And that's the whole secret about Mandelbrot sets. You just look at the results of those 2 formulas in order to decide which color to give a point. And if those formulas go to infinity, you color a point a given way. And if they don't go to infinity, you give it another color. And that's the whole secret about it. So let's implement this. Okay, let's start with dropping it down a grid. So we just have a plane and set that on the XY axis, scale down its size, and increment its subdivisions. Like so, that we have some points to iterate over, or even increase them a bit more, like that. To that, we're going to drop down a point wrangle. And what we're going to do today in VEX is, for the first time, we're going to try to implement our own custom function. Sounds scary, but it is not, and it's very useful. A function in VEX is a thing that you've already been using. So like if you say PCFind to find certain points, or if you use add point or remove point, something like this. These are all functions and they're built into VEX. So someone took care of building those functions and predefining them. What we want to do today is write our own custom function in order to evaluate if one point in our plane for these Mandelbrot formulas tends to go to infinity or not. I always start out with just commenting that this part is for the functions. So my function definitions are going to be here on the top. And I'm going to start by defining my function with the word function. And what I have to specify now is the data type my function should return. And in our case, our function should return an integer. Then the name of our function, in our case, let's call it Mandel. And then the arguments our function needs to work. So, for example, if you have add point or remove point, you need to give the function the arguments of in which geometry it should add or remove a point and the point ID, for example. In our case, we want to give it 3 floats. Let's call them x0, y0, and z0. And for now, I would only need x0 and y0, but for later, for 3-dimensional cases, I'd like to add a z0 as well. Also, we like 1 integer, like that. So this, when I hit apply, it should work. Which is warnings, yeah. So this is my basic function definition. So again, with function, I'm telling VEX that right now I will define a function. The function will return an integer value. This is the name of my function, and these are the values that I need to give my function when I call it in order for it to work. So within the function, I'm first going to define some variables here, some floats, x, and we set that to 0 by initializing it, y, z, x new, y new, and z new, And that's it for now. Also, we want to initialize an integer. Let's call it I, like that. And the first thing we'd like to do in our function, except for defining variables, is write down these values coming in here. So x0, y0, and z0 to x, y, and z. In theory, I can spare this here. Let's just not do it like that and just do it like that. So now x, y, and z contain my values that I pipe into the function here. And now, in order to check if my Mandelbrot formulas tend to go to infinity or not, what I'm going to do is I run over them multiple times and check after each iteration if they went over a certain value, so if they became quite big or not. And when they become quite big, I will just exit that for loop. Okay, let's go through this step by step. Just going to start by dropping down a for loop. And I is my iterator, so if I say smaller than, and this is one of the values that I can define when calling the function. That's why I defined Imax up here. So if I is smaller than Imax, just keep going and increment I. So again, what this says is, execute this loop while I is smaller than Imax, and for each iteration increment I by 1. So what we're going to do first is execute our Mandelbrot set of functions. So the function for x was x squared, so x times x, minus y squared, y times y, plus x0, like that. The function for y was 2 times x times y, plus y0, like that. So we calculated the formula, and after we did that, we're going to check if they are really big, so if this formula is already converging to infinity, and we're going to do that in a really lazy and sloppy way. So we're just going to check if x nu squared, so x nu times x nu, plus y nu squared, y nu times y nu, and we're just going to square them so that we don't tend to get negative values. If those get really big, then we do something. And really, really big in our case, and we're being really sloppy about this, is let's just check if they're bigger than 8. So if that is the case, we can already exit that whole function and return a given value. And again, in our case, our function should return an integer. So if this formula tends to go to infinity, if we check that, if it gets over 8, we can just tell the whole function to return a value with return. And the value it should return is I, like that. So if this condition is met, so if these two formulas yield a value over 8, the whole function just returns I. And I, in our case, is just the current iteration number. Okay, after that is done, I want to write my new x and new y values to the old x and y. I'll just do it by that and that. And if this formula within this loop didn't go over 8, so after this loop is done, we're just going to return the maximum number of iterations, so in our case, Imax. And this is the whole function. So again, let me explain what we did here. We defined the function that we're calling with these arguments, set up the variables, initialize them to the values coming in here, and then set up a loop that iterates a given amount of time, a given number of times, calculates those formulas, checks if those formulas get big, and if they already tend to get big within this loop, it just returns the current iteration. And if they don't tend to get big within that loop, it just exits that loop and returns the maximum number of iterations. In other words, what this function will return for a given coordinate is how many iterations it needs for the set of formulas to go to infinity. So let's put that to use. So this was my functions definition part, and as with it, I'm gonna just declare my main program down here, and this is just for better legibility. And what I'm gonna do is, I'm gonna call the function Mandel, and I want to give it those values. I want to give it my current point x position, my current points y position, and my current points z position. And I want to give it a maximum iteration number of, say, 6. So Let's hit apply, and that is working fine. Okay, so nothing really happened now. So when I want to visualize those formulas, I want to check if this function ran the maximum amount of times, so like these max iterations that I'm giving it here, or if it already returned something before reaching those maximum iterations. And the way I'm going to check that, again, is with an if statement. So if this function here returns something smaller than, in our case, 6, because that's the maximum iterations, we know it already exited here, so we know this tends to infinity. And we want to do something. If that's not the case, we know this function ran through without going to infinity. So let's do something else here. And let's just set the point color to something. So let's just add the vector cd here, and in the case that it exited before reaching the maximum amount of iterations, let's just set the point color to 1, so to white. And if it ran through all the iterations, so if it does not go to infinity, let's just set the point color to black, like this. Okay, let's hit apply, and that looks somewhat like a Mandelbrot figure. So let's just save that, and let's adjust our grid or grid position here so it matches the whole figure, something like that, and increase its subdivisions so we get a much more detailed view. Something like that. Okay, let's go back into the pointer angle. This looks not as detailed as we know the Mandelbrot figures that we come to see from the internet. And one parameter to adjust is the maximum iterations here. And so I don't have to exchange those two numbers here. I'm just going to do that with a variable. Again. Let's call it like max iter. And in our case, let's call it 6. Like that. Like that. Hit apply. Okay, same thing. And now let's just increase it, say, to 16. And now we suddenly see those details emerging here. And if we increase the subdivision of the plane even more, we can get more details out of this, or increasing the iterations. Something like 32. So we get increasing detail here, 64. At the cost of a slightly higher runtime, but yeah. So this is how you basically calculate a Mandelbrot figurine. So this is all good and nice, but what if we want to turn that figure into a 3D object? Well, luckily some incredibly bright guys came up with a formula for turning that Mandelbrot set into a 3D figure. And one homepage that explains the whole process and the whole math behind it and the whole thinking behind it really well is this page here, and I'll link to it in the description. But what that has is, on the one hand, an explanation of what's actually happening there, and, even better for us, when we scroll down here, formulas of how this thing is calculated. And not only formulas, but also a snippet of pseudocode. And pseudocode is a really nice thing, because for understanding pseudocode, you don't have to be able to read math. So let's just take this code snippet and implement it in Houdini. Copy that, head back into Houdini, and let us modify our function first. As I mentioned previously, I already took care of piping in 3 dimensions in that function, but I think we need another few variables for this to work. So if I'm just gonna, maybe up here, just comment out those few lines, and these are the formulas that we're gonna calculate. So I'll need some values here. I need some variables here. For example, n, and let's just set it to 8 for now, and maybe change it later. We need an r, radius theta. We need phi, and I think that is it. And then down here, let's comment out our Mandelbrot formulas. And let's write down our Mandelbulb formulas. I think we can pretty much just copy paste those two. Oh yeah, and the one for R as well. Like that. Yes, that works. Let's just check. Yeah, that's fine. Okay, and now for the formula. We will modify them a bit. So let's just start out with the basic formula. So we call it x new. And we will have r to the power of n, and we're just going to rewrite that as POW r comma n times sinus of theta times n times cosine of phi times n, like that. And what we do here is, what we're looking at here, at this part of the formula, when we compare it to our Mandelbrot formula, it is only this first part. In order to iterate over it, we'll have to add the x0, y0, and z0 respectively to the formula. So let's just do that and add the x0 to it, like that. I'm going to do the same for the y new. So we'll still have the power of r to the n times sinus theta times n times sinus of phi times n plus the y0, like that. And same goes for the z new. Plus z0, like that. Let's hit apply. Yes, that's good. Okay, we have to take into account that we are dealing with 3 coordinates here, so let's add the z new squared here, as well as down here, like that. I think we can dial down the iterations a bit, like that. Hit apply. Okay, what we see here, that looks pretty reassuring because it looks like a slice through that abstract three-dimensional shape that we've seen here. But what we want really is a three-dimensional representation of the whole thing. So not only in a plane, but let's say in a cube. And the way we're going to do that is with volumes. Let's go up here. Instead of using a grid and a point triangle, what we're going to do is we will create a volume first. And let's make it 3 by 3 by 3 units. And say we have a uniform sampling distance of 100 voxels in each axis. So that's going to yield, whoops, let's call it density and maybe initialize its value. It's going to be something like this. Do a smooth wire shade here, and I can initialize it with either 1 or 0. It doesn't matter because I will calculate those values in a wrangle. And the wrangle I'm going to use for that is a volume wrangle, because we're using volumes here. So I just gave the volume a name of density, and I can also make sure that if I didn't give it that name, it will be available in density in here. So just gonna check that box, go into my point triangle node and copy the whole code here. And the only thing that I want to change now in the code is, with that grid, I just changed the color of a given point. Within my volume, what I'd like to do is to change its density. So this was the black part of my Mandelbrot figure in 2D, and now I want that to be solid. So what I'm going to do is set the density in the volume to... No, actually, that's the part that was white. Yeah, actually, when we look at this... So what I'm doing here is in the top part, I'm going to set the outer region. So in my volume, I want to set that region to 0. And the inner region, the region that is black here, I want to set it to 1. So it's solid. Okay, let's go back to the volume and highlight our volume wrangle. And lo and behold, we see some figure emerging here. So let's just save that. And convert that to a VDB. And let's convert it to a VDB and change it from a fog to an SDF, so we get kind of a surface here. And I mean, it's a bit coarse, but we can see the broad structure coming out here. So let's head back into the wrangle. And there are several parameters which I can adjust for. One example is the maximum number of iterations. So the more iterations I give it, the more detailed it's going to be, up to a certain point where it just doesn't make that big of a difference. I'll just stick with, like, say 16 here. The other value which will drive the look of the whole Mandelbulb shape in our case, in our setup, is the n value in our formulas up here. So I just set it to 8. It's getting used through all the Mandelbulb formulas. So what happens when I change it to, for example, 4 is this. The whole shape suddenly looks really different. So the thing I'd like to do is have this number available in a slider in my wrangle, so I can adjust it to my liking without going in here and typing in numbers. And the way I'm going to do that is I'm going to create a channel. And the channel is going to called in, like that. And now all I have to do is click on that button here, and Houdini will automatically parse through this code and create a slider for me, which is called n, and where I can adjust my n value, and it gets directly transposed into the code, like that. So now I have a basic setup. Let's increase the volume a bit, the volume resolution, that is. Let's increase it to, say, 400. And it takes some time for Houdini to iterate through my code and to calculate all those voxels. So this is our Mandelbulb. Let's just save that. And when it comes to rendering this, we could do several things. On the one hand, we could convert this VDB back to a polygon like this, and have a polygonal geometry that we can pipe into our render engine or even export to other programs. But that is kind of clumsy, because that takes computational power, it takes time to convert it back to volumes, it takes RAM, it takes memory. So what I'd rather do here is render this VDB surface directly. And there's a really elegant way you can do that in Mantra. Going to the object level and just going to create an environment. And I will add a HDRI, that. Also going to add a camera just by control clicking on the camera symbol. Lock the camera so it pans with me. And now, in order to be able to render those volumes in Mantra, I need, of course, a Mantra node in the output. Let's just add that and set the rendering to physically based rendering, and maybe give the Mandelbulb materials. So in shop, let's just create a Mantra surface, just a basic Mantra surface for now. Go back to the object level, highlight my, let's call this Mandelbulb or Mandel, highlight that, and assign a material to it, like that. Okay, we could feel tempted to immediately go to the render view and hit render now, and when we do that, and what we see here is the rendering really has this coarse approximation that we know from the fast preview of VDB, so it didn't take into account the actual surface of the VDB SDF. But we can force Houdini to regard that SDF by going to the object level, then selecting our Mandelbulb object and going to the render tab and into the sampling tab. And what we need to do now is add some parameters here, and we do that by going to the edit parameter interface, and we go to the render properties tab, and let's filter this for volume. No, not like ball. And what we find here is within Mantra, within the sampling folder, and let's close that down here. So within the sampling folder, we see two parameters that we need. One is the volume isosurface, and we're just going to drag that over here to the sampling tab. And the other parameter that we need is the volume density here. So let's drag that over as well, say apply and accept. And we have those two parameters exposed here. So volume density is set to 0 and volume isosurface checked on. And when we hit render now, we see that mantra is actually regarding the sign distance field that we have in the VDB and is generating this surface out of a volume. Exactly what we wanted. And one thing that we can do to add a bit of a speed up to this algorithm is just take these two nodes here, just copy and paste them, drag them over here, and just set this volume's resolution here to something really low. Say something like 50. And what we're going to do here, what this allows us to do is just really quickly calculate a very rough Mandelbulb shape in here. Let's set the sampling even lower to something like 40. And we'll increase the size of the volume because we want to account for different shapes of the Mandelbulb. So for example, when I set the n value to 2, this Mandelbulb gets quite big in its area. Like here it's really pushing the boundaries of a 3x3 volume. So let's set this to 5. What I want to add now is a volume bound node. And pipe that in here and highlight it, and what that will give me when I dial up the bounding value just a tiny bit, something like that, it will give me a box which will enclose only the active parts of this volume. So let's expand this bounding box just a bit by adding a peak sub here with just a small value here, a bit bigger now, like that, yeah. And thus we just really quickly generate a bounding box for the volume, an approximation for that. And what we're gonna do now is use that bounding box to drive the volume here, to set up the high resolution volume, which has got a way higher resolution than the previous volume. And we're gonna use this high resolution volume of the correct size to now calculate our Mandelbulb into it. Let's just choose sampling distance by size, and let's set the division size to something a bit smaller. And let's highlight the volume wrangle. And maybe I set the division size a bit too small because that's taken an awful long time here. So maybe let's stop that simulation and increase the voxel size a bit. Something like that. Exactly. Oh, now what I want to take care of is that the n values always have the same value for the main calculation and for the auxiliary calculation, and I do that by just going in here and copy the parameter, and in our auxiliary calculation I just paste it as a relative reference here. So now when I highlight our final output, we see that the volume has exactly the bounds of the final Mandelbulb shape, even when changing the n parameter. See, so the bounding box changes its shape and its dimensions as well. So to sum up, what we learned today is, on the one hand, we learned to write functions, custom functions in VEX. We learned how to directly render sign distance field volumes. And we learned a small trick to speed up the calculation of a Mandelbulb. And as always, if you guys create any artwork using that technique, please just send us a link. We're always intrigued to see what you guys come up with. So I hope you had fun with this. And it's cheers and goodbye.